we have Angela here yet? No. You have no trouble with internet, correct? Usually?
Yeah, mine works really good.
Good. Good. My own also usually works. I think only once I think it has given trouble. Once or maybe twice, yeah.
Yeah.
Usually. Yeah.
Are you in Neckers right now?
No. I'm at home actually.
Oh, really? Oh, okay.
Yeah. Yeah, Neckers was a possibility, but it's easier to do this at home. I think if you're in Neckers, you have to inform the appropriate people, I suppose. Yeah, why did I decide to do it from home? Yeah, I think I didn't want to drive every day, I suppose. Yeah. Probably it could have been better because then you have more board space. I could have been in room 410, and that would have been nice.
Yeah.
Yeah, probably.
Yeah, one of the whiteboards actually. I thought you were at Neckers. I always thought you were at Neckers because of the whiteboards behind you. I figured it was a room there.
Yeah. That's. I mean, this. I bought this right after, right during this break when all this was decided.
Okay.
So immediately I went and just bought 3 of them. And yeah, I think I think this is the reason why I decided to do it from home. Then I put you guys on TV.
Right.
And then I have a little bit of classroom experience. I think in this class it works well because both of you guys use video, but the whole purpose was lost when undergraduate students just come and mute themselves and switch off their videos. So my whole purpose of making it a classroom atmosphere failed right there.
Right.
And I didn't want to insist on that. Yeah. Hi, Angela. See you again.
Hi.
Yeah. Okay, so there was this question raised by Angela in the morning that how many more homeworks. So I decided, yeah, we will have only one more homework due, which will be due on Thursday, next Thursday. So we'll have one homework due. I'll pick a particular homework which sort of is more representative of the whole topic and proceed accordingly. Okay. So that should take away a little pressure, I suppose. Because I can understand that in the last 2 weeks, probably everyone piles homework, and yeah, so understandable. Yeah. Okay. So, any comments or questions related to what we're doing as of now? Anything else?
I did have a question about the homework that was due today, homework 7. The first question, I believe it asks us to start with the Maxwell's equations, and I think derive some wave forms of them, but to do so without invoking any potentials. And I was looking through the previous lectures to try to see where we went over that, and all the stuff I could find, and maybe I just didn't scan thoroughly enough, but all the stuff I could find seemed to show us only doing so with the use of potentials. And so I'm wondering if there's a specific lecture that I should be looking.
I don't think we covered it in the lecture, but start from the math. Okay, I can. Yeah, how about this? I can help you guys with it, right? Yeah. So, yeah. So let's let me a few steps I can go with this. Yeah. Yeah. Let's do this. Okay, so we have one of the Maxwell's equation tells us that what's that last one? Del cross B is equal to del cross B is and then there is mu naught times epsilon naught, which I can write it as C square times d by dt of electric field plus mu naught times J, correct? That's one of your Maxwell's equations. Since I'm interested in a wave equation sort of form, the right thing to do is right away take the cross of this equation, take a curl. That's equal to, curl goes through, so I get 1 over C square d by dt plus mu naught times del cross J. Agreed? I can use the back cab rule here. This will be the gradient of the divergence of magnetic field, which of course is 0, minus of the Laplacian of the magnetic field. With me? And here I can use the second Max or the third Max. Yeah, no, it's the second Max, however you write it. One of the Maxwell's equation tells you that this is minus of time derivative of the magnetic field, which gives me minus 1 over C square d square by dt square of the magnetic field is equal to mu naught, plus, right? Mu naught times curl of the current. Great. Which is your wave equation. Times magnetic field is equal to mu naught del cross J. Agreed? And the same thing, any questions on this? Same thing you can do starting from the other equation. You would say del cross E is equal to minus time derivative of the magnetic field, correct? That's one of your Maxwell's equation. Again, do the same idea. Take the curl on both sides. And this gives you minus d by dt of curl of the magnetic field. So very similar situation, except that the divergence of the electric field is not 0. So this is the divergence of the gradient of the electric field, which is not 0 this time. Earlier magnetic field, the divergence of magnetic field was 0, minus the Laplacian of the electric field. And now we use this other Maxwell's equation, other inhomogeneous Maxwell's equation if you want. And this is minus 1 over C square time derivative square of the electric field. That's one piece. And we also have mu naught J, right? So it is minus mu naught times time derivative of J. Else, this is nothing but rho, using Maxwell's equation, rho over epsilon naught actually. And this too gives you the wave equation. Take this onto the right hand side. So the gradient of the charge density and the time derivative of the current shows up, and that is exactly that is needed in there, and is written in a form so that epsilon naught is highlighted instead of mu naught. So that's the only difference. Okay, so that should take you there. So the basic, I think probably it's tricky because to see through the fact that the Laplacian can come out of a curl is not immediate unless you have too much experience in there. But that's one thing to remember always. It helps a lot that you can get a Laplacian out of a double cross product. Back cap rule helps. Okay. Questions on that? Okay. So yeah, that should help you with that. And how was problem 2 and 3s? Was that okay? Doable, or have you guys reached there?
I started working on 2. I think 2 will be fine. 3 though, I don't. It seemed 3 seemed new. Like I don't recall ever seeing the content of problem 3.
Oh, I see. I see. Okay, no, that's an important thing. So let's. We did do it. Let's see. So. Maybe I'll use the other board. Remember, we used the idea that, what should I say? Let's say you have, I'm going to build the problem x minus 2, x minus 3, let's say. That's delta of x squared minus 5x plus 6, correct? Divided by or times, let's say, what should I put here? Sine, let's say, sine of pi x, and let's say dx. And this could be minus infinity to plus infinity. And let me also put pi by 3 there. Okay, so that could be a random question I just constructed. Okay, clear? So the procedure to proceed in this kind of scenario is, this is a function, treat this as a function, look into the argument of the delta function. There are 2 steps. First step is whatever is the argument, you set it to 0. To ask for what x is the argument as 0. So that involves solving a polynomial equation. In the problem that is given to you, this is not a polynomial, it is a function sine x. That means to say that it has infinite roots. If I tell you that sine x is equal to 0, it has infinite roots, right? Sine of x goes to 0 at infinite places, like pi, 2 pi, 3 pi, 4 pi, it goes at many places. So it is a extension of this. There are only 2 roots here. There are infinite roots. In this case, it is at x equal to 2 and at x equal to 3, correct? When x is equal to 2, 4 minus 10 plus 6 is 0, and when x is equal to 3, it is 9 minus 15, and again it is equal to 0, correct? The second step is to find the derivative of this argument. You say it is 2x minus 5, right? That's the derivative of this argument. Okay, so in the problem, this is defined as f is equal to 0, and this is the derivative of f of x. Okay. Now, how do you evaluate this integral? Let's say this is I. If I were to evaluate that integral, I'll do whatever is a function, I will set it to 2 first, sine of pi over 3. I'll set x equal to 2 first. And then I need a coefficient for that. The coefficient is decided by evaluating the function 2 of x at the same point too. So this is 2 minus 5. But this could be negative, so I have to take a magnitude of this. Okay. Is that clear what I did? I took the derivative and evaluated it at x equal to 2, at the root. The same thing here. So this time it is the other root. So it is 3 divided by 2 times 3 minus 5. And so on. So this is now I can evaluate this as a number. Okay, maybe this is not a very good exercise. Maybe this is 0. I don't know. Okay, but in your problem, in your homework problem, there are infinite roots. So this is a series now. There's +1, +2, +3. There's lots of them there, and you have to put them all together. That's all you have to do, and you have to identify that it is actually an actual number. Let's see. In your case, and okay, maybe I can give you a hint that there is a series called zeta function. Have you guys heard of zeta function?
Has it got something to do with the gamma function as well? No.
Yeah, very similar to gamma function, but it's not the same. It's very similar. It is usually, if you're studying these things, first you study gamma function, then beta function, then comes zeta function. And that spirit, yes, that's very much related. But it is very popular. It has a very, this is called Riemann zeta function. Are you aware of what is a Riemann conjecture?
Name sounds similar, but I don't remember what it was.
Okay. Yeah, you guys should know, and since you guys are young, you should attempt it at least once in your lifetime, or reasonably quickly, because usually they say that the chances of solving a problem, solving an important problem, is high when you're young. So since you guys are young, so you should attempt on it reasonably quickly. So here is the point. So first let me define zeta function. So zeta function is, if you think of it as just as a series, it is 1 over 1 raised to yeah, so this is 1 raised to s plus 2 raised to s plus 3 raised to s plus so on. Okay, so that's a reasonably straightforward series, and maybe you've heard of this. Now calculate what is zeta of -1. Can you write the series there? Right, zeta of -1, if you notice, is this is also s, by the way. So put s equal to -1 in there. So this becomes 1. Second one is 2 raised to -1, which can be brought up. So that's 2. Correct? And third one is 3. And fourth, and what is that equal to?
1 by 12.
By 12, yeah, -1 by 12, good, right?
Yeah, minus.
So, and that, so now how can that be true? All that, leaving aside all that questions, right? This is a series representation. This series is true only for s greater than or equal to 0. I think it's greater than 0. This is true only for s greater than 0. Okay. But you can find an integral representation for this, which is valid even for s less than 0. In fact, almost everywhere on the complex plane. Okay, so I think if I remember this correct, it is 0 to infinity dt over t times t raised to s, and probably there is e raised to t minus 1. Yeah, e raised to t minus or plus 1. I don't remember whether it is -1 or +1. Okay, so that's the integral representation, and this is valid for all s's. So you can think of s being any complex number and you can evaluate this. Okay, so it seems like a very just a way of defining a function, pretty much like a gamma function. But now here is a conjecture of Riemann. So let me put this with me till now, like at least a little bit of motivation that what is a zeta function, like it's a function defined this way. Now whatever this is a function on a complex plane. Right, so there is an S, this is a real part of S, and this is imaginary part of S. Okay. And you ask the question, for what values of S does this go to 0? Okay. You ask the simple question that for what values of S on this complex plane does this function go to 0? Zeta function goes to 0. It's like saying sine of x is equal to 0. For what values of x does it go to 0? Correct. So you ask that question, and it is hard because it's an integral relation. It's hard, but Riemann gave the following conjecture. He said that all the roots of this equation lie on a line which is exactly at s equal to half, like on a line that is vertical, imaginary line. If you ever find a 0, whenever it goes to 0, and they differentiate between trivial and non-trivial, 0, trivial 0 means it is immediately 0. You can kind of know that it's going to be 0, which is on the negative x-axis, there are lots of zeros because gamma function has zeros in it. Without going into that details, the non-trivial zeros all lie on the z equal to half, the imaginary line connecting that. And it turns out, as of today, that every root that has been found for zeta function has always stayed on this line. And this is considered in mathematics the most or the longest standing unsolved problem, in a sense. Like usually someone poses a problem, and if it is popularized sufficiently, smart people come and attempt on it, and they solve it, usually 50 years, within 10 years typically. If a problem can stay at a popular front unsolved for 10 years, that's big. So this is for the last 150 years or so, this is unsolved. And there are lots of prizes associated with it, lots of $1 million of solved prizes. But more important than that, other than the prizes and the recognition that one goes after, it's also important that this has a direct connection with prime numbers, like y prime, whether you can find you can say a closed form expression for finding the prime numbers. Like we don't know, given a number, there is no simple way of checking whether a number is prime or not. Does that make sense? Like given a number, it is not easy to say whether a number is prime or not. You have to go and try it out. That's trial and error. Like computer checks every number, divides it by every number, checks it, and tells you whether it's a prime or not. That's the only way possible. There is no other way to check whether a number is prime or not. So if you can come up with an algorithm to check if some number is prime or not, it has very big implications. For example, your password can be, all your passwords will be useless after that, because our passwords depends on the fact that this is a hard problem. So it's used as a key, like lock and key mechanism. Since it cannot be solved, you know that computer cannot solve it. So you know that your passwords are safe. But if you can solve it, then the whole basis of that logic goes down. That's the same importance you give to the quantum computers also, because it becomes an easy problem afterwards. It's a hard problem in the sense it will take forever for the computer to solve it. But if you make it a faster algorithm, then that's also one way to do it. But of course, you can escape that by just making your password longer. Just make it long enough that quantum computer also cannot solve it. So does that roughly at least address the, at least pose the problem? And again, since you guys are young, you should attempt on it. Okay, so it's just finding the roots. How hard can it be? Okay, so with the digression, and yeah, with that, you should be able to do the problem. The problem is constructed based on the zeta function, but doesn't use any serious properties of that. It's just a definition of zeta function that it uses and nothing else. Okay. So you should see this series showing up, and then you just identify what that is. Okay. Okay. Let's proceed. Okay. Okay. So what we showed is that we talked about radiation. So starting from Maxwell's equation, we showed that in the radiation approximation, so radiation involves the idea that there is a source and all the R primes, which we have been using consistently to represent sources, and the observation point R is very much far from the source point. In fact, it is the time that is important. We say that so R minus R prime is very much large compared to, so let's say C, right, divided by C, is very much large compared to the time associated, the characteristic time associated with the system. Usually there is a time associated in the sense if there is an atom, it could be the periodicity of how much time it takes to go around the proton, or better, anything that has to repeat after a while. It doesn't have to be periodic, but usually you can get a time scale in the problem. If there is no time scale, then it doesn't work. Then there's a good chance that you cannot do a radiation approximation on it. But typically, especially at in a system like this, you can always find a scale in time. In that case, the Maxwell's equation can be solved actually for any arbitrary distribution of charges, and we showed it this depends only on the current, or we could express it in terms of current alone, and the magnetic field, and notice I multiplied it by C, so that is just to make the dimensions clear. Remember, force on a charge is Q times the electric field plus Q times V cross B. So that tells you that electric field has the dimensions of velocity times the magnetic field. So that's the idea of keeping the C there. So then magnetic field, electric field, and speed of light times magnetic field has the same dimensions. So the magnetic field in a very far region, remember our approximation is that R is very large. So in fact, you can take it large enough that it is at infinity. So by radiation, always the understanding is that we are talking at infinity. So we are in the very far region. It's almost like looking at stars. Whenever you're looking at stars, where is the light coming from? Stars are so far away that we never bother to talk about which star is closer and which star is farther. All the stars are on a dome, right? On a sphere of infinite radius. So similarly, radiation, so there is a region here, put a dome around it, and we are talking about R tends to infinity there, and in the leading order we do pick out R. So this is given by, this is equal to, we set minus R hat. So R hat is in which direction you're looking, right? So there is a charge distribution, and r hat is in the direction of the observation, right? And that observation point itself could be moving, right? Or sorry, not moving. It could be anywhere on that dome. So that's equal to crossed with. So what does this magnetic field depend on? On the very far region, and depends on the current density in here. And we expressed it in the form mu naught over 4 pi. And there is 1 over r. This is your leading distribution. There is an r dependence in there, but that's just the 1 over r dependence, and it will go away. This is the magnetic field, but we typically we are interested in the energy. Energy will have 2 times r, and it will cancel out. So we will see that we will capture the finite part in there. So simply because r is infinity, you shouldn't think that, oh, this is going to go to 0. So that's 1 over r, and then we have an integral. So integral over the sources, and it is time dependent. So it is time derivative of j evaluated at r prime, comma, let's say t of r. Right? Since there is no space, I wrote t of r. I can write it explicitly also. And t of r is a retarded time. So t of r is t minus the leading retardation comes from how far it is. Light takes time to go from here to there, from the origin all the way to infinity, since r is very far away. And also the next leading contribution is r hat by r prime over c. So there's an r prime also sitting in. So that's what we showed. The magnetic field is dependent on the derivative of the or the contribution coming from the time derivative of the current density. So if current was not moving in time or not changing in time, then there will be no radiation, or that means to say no magnetic field to that. And its direction is given by whatever is the direction of this rate of change of current crossed with the direction of observation. That's important. Okay. Once we have this, we can get the electric field also. Electric field is equal to minus r hat crossed with the magnetic field. Okay. C is traveling around with the magnetic field just for dimensional purposes. So once you have the magnetic field, you immediately have the electric field. It is exactly the same magnitude, just its direction is perpendicular to the magnetic. So for example, if you were here, that's your source, and that's your r vector r, or which is also r hat, correct? It depends on j. So let us say this is your direction j. Right? So that's could be your direction of whatever this derivative of j is. Right. So that's your source contribution, whatever that direction whole thing is. R crossed with that gives you the magnetic field, but then you have to negate it, so it goes in. So the magnetic field goes in here. Right, that's your B. So on the sphere that you can draw at infinity, on a dome that encircles the sources, the magnetic field is tangent to that dome. Always it will be tangent to that dome, and it is perpendicular to r hat. It depends on in what direction at a certain moment of time this whole integral is. So because you're adding so many vectors, there is a lot of contribution coming from, but this is that resultant of that whole thing. Whatever that vector is, and we will talk about a simple situation when there is a single point charge, and there will be a nice interpretation in there. But as of now, very generally speaking, that's a vector, and cross of those two vectors decides your magnetic field. And once you know the magnetic field, R crossed with magnetic field, so that's your magnetic field. So electric field should be this way, but negative of that. So that's your electric field. Both are tangent to the sphere of infinite radius enclosing the source, or the dome that encloses the source. Clearly, if E is this way and B is going into the board, E cross B will be in the direction of R, and which we can write here again. So this will be also given by C cross B or T. I can again write it as, this is of course R cross with the current density, but starting from here, if I use the back cab rule, I can again show that C cross B is R hat crossed with electric field also. Right? And if I were to do E cross B, I will get the same R hat. So this is your, so these are the requirements for, or this is your equations that govern radiation. Right? Radiation is governed by these three equations. In fact, first one is sufficient, rest everything follows along. Okay, any questions on this? Other, this is the summary of what we did last time. Okay. Let's take the simplest scenario, right? What's the simplest way of generating this current? Anything that generates a current, any charge you can think of that generates a current carrying wire is the simplest. That is how an antenna is generated, but there is a simpler than that. Let's think of a point charge that is moving. A moving point charge has a current associated with it. So let's talk about a moving point charge, right? Simplest example one can think of. And for a moving point charge, I have my current given by current density of a moving point charge, T, is equal to charge itself times its velocity. Right? It depends on Q times the velocity of the charge. Since it's for the charge, I'll write that as Q. So that's a subscript Q representing that as the velocity of the charge. It depends on time in general. Right? Velocity depends on the time, and times delta function. Like this is this has the units of per unit volume, current per unit volume, and this is R prime minus, and this exists only where the charge sits. Otherwise it is zero. Everywhere it is zero except where the charge sits. And where is the charge? That's decided by the position of the charge, which is again time dependent. Okay. And the time dependence is important because the time dependence decides the retardation part, right? This whole radiation has a lot to do with retardation. So that's crucial there. Okay, so that's the description of a moving charge. Substitute this in there, we get the solution for the radiation from a moving charge, right? And this could be an arbitrary motion. We are not saying what exactly is the motion. If it is uniformly moving, that's simple. There is no time dependence. It could be accelerating. It could be going in a circle. It could be going in a very complicated curve. We keep it very general at this point. So substitute this in the top expression, and we get the magnetic field due to this. Or yeah, so let's do the magnetic field. So that's R comma T is equal to minus R hat crossed with mu naught over 4 pi times 1 over R, and that is d cube R prime. Time derivative can come out. The way I can write this is that take the time derivative and substitute t is equal to tr in there. Let me put the time derivative out for a moment. Okay. Oh, or maybe I should be careful. Right. So this is d cube r prime, and that is q of time derivative again. Sorry, time derivative of q times vq at t, and this whole thing r prime minus rq of t. And it is important that this whole thing is evaluated at t equal to the retarded time. Now this brings in a complication that the retarded time has r prime in it here, and I have to replace, when I'm doing the integral, I have to solve for this r prime, and this rqt will also have an r prime in it. Right, so it involves the same, we worked on a delta function problem. Remember that at what points does this delta function contribute? It contributes whenever this is equal to 0, and that might be a complicated polynomial. But let's make the assumption that the retarded time is equal to, which is equal to t minus r over c plus r hat dotted with r prime over c. Okay. This, if the charge is moving slowly, if the charge is moving slowly, the r prime gets contribution from the speed, because the r prime gets replaced with the position of the charge. So if the velocity of the charge is very much smaller than the speed of light, right, because there is a 1 over c there, if the velocity of the charge that we are talking about is small, which is reasonably okay, even an electron at its highest point usually travels only by a fraction of the speed of light. So even for that, that is good, but most of the charges move around significantly slowly. So it is okay to make that approximation, but it is also true that often we do have situations where it is moving with the speed of light. So this is in that approximation. So this is called a non-relativistic approximation. So we should be careful what this implies. So a more complicated expression requires a lot more work. And if you're, for example, wanting to study a charge moving in a CERN lab, in an accelerator, there it is going with a significantly high speed, and this approximation probably is not very, very appropriate. So in the non-relativistic regime, this third term can be dropped, and we can simply write t minus r over c. And then it is easy, because then there is no r prime sitting in there. The delta function is immediate. And in that particular case, I can write the time derivative comes out. Right. In that particular case, this delta function integral is immediate, because delta function really replaces all the positions with its with the position of the charge, and the time dependence is not a complication in there, and that's equal to minus r hat crossed with mu naught over 4 pi times 1 over r, and this simply becomes q times time derivative of the velocity of the particle evaluated at t minus r over c. So it's not the time at which it is supposed to be there, it is retarded by the amount r over c. This is now having only one parameter here, So we don't have to worry about the partial derivative. Partial derivative is the same as total derivative, and derivative of velocity is acceleration, correct? So it seems like the magnetic field depends on the acceleration. So let's see how this works out. So the magnetic field, C times the magnetic field at on the infinite on the domes, which is infinitely far away, is equal to minus r hat.
Can you move the?
Oh, move the board, of course. Sorry about that. Yeah. So I was just rewriting that equation. So I have minus, I can write this as minus mu naught over 4 pi 1 over r, correct? And then there is q times acceleration, or r hat, or let's say q over r, and then r hat crossed with the acceleration of the charge evaluated at t minus r over c. That's it. That's what the magnetic field depends on. The electric field will be the cross of this, and so on. So how does this look like? So let's say that is a positive charge here, and it's accelerating in a particular direction. That's your acceleration, correct? That's your acceleration, and your observation point is very far away. So that's your r hat. And this angle tells you where the what the radiation is going to be. Clearly, this depends on sine theta, correct? R cross. So the magnitude of the, so let me write this as a magnitude of the magnetic field is going to be equal to minus mu naught over 4 pi times q over r times the magnitude of the acceleration evaluated at t minus r over c times sine theta, correct? In what direction is the radiation going to be maximum? If this is my magnetic field, in what direction is the magnitude of the magnetic field the largest?
Perpendicular.
In the perpendicular direction. And what if you look at the radiation in the particular direction of A?
0.
No radiation, actually. So that's kind of is the beginning, or a kind of small glimpse of the fact that if you make an antenna, it is very orientation dependent. Like if you lived about 30 years back, I don't know these days, there are those antennas.
Mathematics of how the radiation is maximum in a perpendicular direction, but what does it physically mean? Like along the direction of the acceleration of the particle, there is no radiation. Why is it maximum? Why is it maximum in the perpendicular direction?
Because of the sine theta.
Okay, yeah.
Like this is the observation point. So for example, this is the observation point, right? R. So if you stand here and observe this, there's a lot of magnetic field. If you were to stand here and observe the charge, you don't see the charge at all. There is no signal coming from the charge. Absolutely no signal. You won't see any exactly vertically. If you are slightly off, you'll get a little signal, and so on. This seems to be magnetic field. Maybe I can convince this better. Let's talk about usually as a, if you're making a device, of course, you can sense the magnetic field, but typically you're talking about energy, right? How much radiation is there is talked about in terms of energy or power, right? How much radiation per unit time. That's a measure, that's a better measure than talking about magnetic field itself. But if you want to make a device, you will surely make a device that senses magnetic field, correct? So for example, I have done this for a point charge. what you will do, probably either I will do it today or next class. If you make an antenna, that means to say if you make a wire that has a lot of charges moving in it, basically a current moving in it, and you make it oscillate, right? If you want a particle to be accelerating always in the upward direction, that's not practically a practical solution, right? It will run away from the house very quickly, and you cannot go about controlling that. But instead, who says that acceleration has to be in the same direction? Usually what you do is you make this charge oscillate. If this charge is oscillating, or for that matter, it can just have to go in circles. A charged electron that is going around the proton in circles is accelerating, correct? And that acceleration will cause a radiation. In what direction it will radiate is dependent on the time dependence of this acceleration, and at a particular time, it's decided by this configuration sin theta. Does that help? Is that interpretation clear, Anshula? Does that answer your question? Right, roughly? Or?
Yeah.
Okay. But usually it is nice to know how much energy is there in a certain direction. Magnetic field in a certain direction is good, yeah, because you want to make a sensor which probably depends on the magnetic field or the electric field. Usually you're more interested in how much energy is thrown into a solid angle in a particular direction. For example, if you're making an antenna, you would like to design an antenna where there are lots of people living in one corner of the city, less number of people living on the other corner. So if you're addressing to a particular set of population, then you wanted to make it oriented, and you would like to know how much energy is being directed in a particular direction, and then you want power, right? For that, you remember your relation. S was equal, so this was the pointing vector, right? Pointing vector is the energy flux, right? Energy flux, let's call it energy flux, which is pretty much energy per unit area per unit time. Or a better way to say it is energy per unit volume times a dimension of velocity, right? Remember here, where does this come from? Conservation of energy equation was this, like long ago, like we began our course by defining a energy associated with electric and magnetic field U. Remember this? Like maybe, so U was equal to half epsilon naught E square plus 1/2 mu naught B square. That's the energy density. In any space volume, there is so much energy per unit volume of space-time. Correct. And S was equal to, S I will write it here. So that was E crossed with H, but I'll write it in terms of B because we are writing everything in terms of B. So I had to divide by mu. So we wrote it as E cross H when we defined it. So that's energy flux. What does that mean? How much energy is going through a particular area? Choose the area of your favorite area per unit time. So energy per unit time per unit area. So this is energy per unit area and per unit time. Okay. And we are interested in calculating the power per unit time, right? So we don't even care for area. So let's see how you would do that. So the power would be, you just have to integrate over the whole area. So let's do this as, let's enclose this whole charge with a sphere. That's what we did, right? We talked about a whole dome that is enclosing the charge. So if I were to integrate over all the radiation that is coming all over the charge, that will be equal to integration over the sphere or the dome of infinite radius, right? And that's dA. So this is closed integral of dA dotted with dA is the surface here. So let me, since I used acceleration as A also, So let's use S here. S dotted with, oh, S is also not good because we have the pointing vector. So let's say dA, the capital A, dotted with S, right? So that's power. Basically, you're integrating over area. So that's energy per unit time. So that's a power. Okay, with me? So we know the electric field and magnetic field from any charge distribution. And now we're talking about power that is radiated into a certain region. But this is now the total, we are calculating total power, total energy per unit time. If you are very far away, the radius is a radius square. So this is nothing but, and radius is fixed at that large distance. So that's r square. Remember 4 pi r square, and you integrate over that whole sphere, which is the solid angle. So integrate over all of solid angle. What's the direction? It is r hat, right? Dotted with S. S is E crossed with B. That immediately lets me define the power radiated per unit solid angle. Like this is the total power radiated all over the dome. But if I were to take out the integral, I get the power per unit angle, or per unit solid angle. That's equal to r square times r hat dotted with S, but S is nothing but E crossed with B. And that is a mu naught, which I'll pull it out in front. Correct? That is a cross and a dot. I can swap it, like, so it becomes R cross E times dotted with B, but R cross E is nothing but B itself, right, with a factor of C. So let me move the board space. So that's equal to, remember, R cross E is equal to C times B, right? We just, we started the lecture with that. So the magnitude of B square comes in, right? So, and there is a C that shows up. So I'll write this as R square over mu naught times C. So R square seems like it's infinity, but each of this electric and magnetic field has an R in it. So this is C times B dotted with C times B. So that's a square of that. And each of the magnetic field has a 1 over R in it, right? So if you like right here, you can see that, right? There's a 1 over R in it. So the R square actually cancels out. So let me substitute that in there. So since it's a square, the negative sign doesn't matter. R square cancels that out clearly. So it is mu naught over, oh, first let me write the mu naught C. So R square cancels out. There is a 1 over mu naught times C and C times B. So it is mu naught over 4 pi times Q over R. I'll cancel that out in a minute. And then I have R cross, R hat cross of acceleration, which is evaluated at T minus R over C squared. Squared in the sense of total squared. And that is R square also. Clearly, the R square cancels out. So that's the point, that it is finite on that infinite dome. Like you would think that something, when you're a charge that is oscillating, it won't reach infinity, right? Typically, that's the approximation we make, that electric field is 0 at infinity, unless it's radiation. So it is very weak surely. It goes down by 1 over r, but that is still energy. Power is still reaching that infinite dome, but it doesn't mean that it's at the infinite region of your universe. It's just that even by the time it has traveled 10 meters, it has not lost everything. So you still have energy left. But what is this equal to? Let's try write make this nicer. Let's express this slightly neatly. Okay. So that is 2 mu. So the power radiated per unit solid angle is equal to, that is 1 over mu naught times c. That is mu naught square, and that is 4 pi square. And that is q square. R hat crossed with the acceleration. I'm going to write that as acceleration squared. So there's a square of the acceleration vector evaluated at the retarded time. That's important. Square. And then there is sine square theta. Okay. So again, that same sine square theta comes in the energy. This can be written slightly differently. I can cancel out one of the mu's, divide by an epsilon naught. So this is 4 pi epsilon naught. I pull that out. And once there is an epsilon naught, I have actually put an epsilon naught in the numerator. That's 1 over 4 pi c cube. So let me write that as 4. So q square over 4 pi c cube. Right? That's a very classic expression where you see a q square over c cube. This is what is called the Larmor formula. Or actually, let me do one more thing. Squared and sine square theta. Again, the same a diagram. There is an acceleration in, it has a direction at a particular time t, and the radiation is decided by this angle theta, and that's r hat. There is no energy radiated when theta is equal to 0. In the direction of the acceleration, there is no energy radiated. Of course, it's in the retarded time, so be careful. Even the direction, you have to retard it. Like if the direction is keeping on changing with time, it is in the retarded sense that it depends on the direction. All right. If that's the energy per unit solid angle for each angle theta, like as we said, at theta equal to 0, there is no energy. At theta equal to pi by 2, there is a lot of energy. But nevertheless, it is good to talk about how much total energy is radiated. And for that, we just integrate, right? So we integrate this over the whole angle theta. Right? So this is 1 over 4 pi epsilon naught q square over 4 pi c cube, and there is no angle dependence in here, so that comes out a, let me just write it as a square, a q square, with the understanding that this is all in the retarded time, and I integrate this over the whole solid angle, which is d phi, going from 0 to 2 pi, and 0 to pi d theta sine theta of sine square theta. Okay. So what's the integral of sine square theta when you go from 0 to pi? This is equal to 2 pi. And this integral, I can substitute this to be 1 minus cosine square theta. And then substitute cosine theta is equal to t, right? That's a standard substitution when you go substitute or do an integral on the surface of a sphere. then the limits go from when theta is equal to 0. So this is minus sine theta, d theta is equal to dt. And when theta is equal to 0, that's equal to, when theta is equal to 0, it is 1, right? When theta is equal to 1, so the lower limit is 1, upper limit is cosine of pi, which is minus 1. So it goes from 1 to minus 1, but then there is a negative sign which flips the sign. So the power is equal to 1 over 4 pi epsilon naught q square over 4 pi c cube. The magnitude of the acceleration square measured at the retarded time, 2 pi times minus 1 to plus 1 dt. The minus sign has been taken care of. And this is 1 minus t squared. That's a straightforward integral. When I go from minus 1 to 1, so that is a t. So how do you do this? So it is t minus t cube over 3. And I have to evaluate this from minus 1 to plus 1. So it is 2 times this evaluated at 1. So it is 1 minus 1 by 3 2. So that's equal to 4 by 3. Right, so this whole thing gives you a 4 by 3, which is 8 pi by 3. So this gives you a total answer of 4 pi epsilon naught q square over 4 pi c cube. That's a q square, and that is an 8 pi over 3. There's a 2 pi here, 4 by 3 from the integral. That gives you 8 pi by 3. This 4 pi can cancel that. So let me rewrite one more step here. So 1 over 4 pi epsilon is there simply because of SI units. And this is 2 over 3 times q square over c cube times a of q square. Just the acceleration decides that. This is the total power emitted per or total energy emitted per unit time. Depends only on the acceleration. This is called the Larmor formula. This played a very important role in the development of quantum mechanics, because the immediate argument is that, so we are going to, if you have a closed system which is accelerating, that will lose so much of energy all the way to infinity. All the way to infinity means to a very far region. So from the system, you're losing it. So let's consider hydrogen atom. In the hydrogen atom, we can calculate how much is acceleration, right? That's a easy calculation to make. So, so take hydrogen atom, and how do you calculate the acceleration in hydrogen atom? How would you go about that? So let's think of a hydrogen atom. So there is a positive charge and there is a negative charge. So you would say mass times acceleration has to be equal to mv square over r, right? Sorry, mass times acceleration is 1 over 4 pi epsilon naught times q1 q2, which is e square over r square, right? So you know those numbers, correct? So let's say this is a. The acceleration we know is 1 over 4 pi epsilon naught times e square over m r square. Okay, and this, of course, we have to say that this r is the size of an atom, correct? We know that that's going to be inside the hydrogen atom. So this r is the size, let's call that r naught, right? the atomic. So put that in, and in fact, this in principle has a number associated with it. Can I write this in a certain sense? Let's see. Yeah, so as of now, let's just put that in. So this is power radiated is approximately equal to, or at this state, exact actually, this is equal to 1 over 4 pi epsilon naught, 2 by 3 q square. Now we are talking about electrons, so this is E square over 4 pi c cube, and AQ square, so square this, E square over m r naught square, the whole square. All these numbers can be actually calculated, and you can calculate how much power is it going to lose. In fact, we can do one more thing. We know how much energy is stored in a hydrogen atom, right? So there is a positive charge and there is a negative charge. How much energy is stored in it? There is kinetic energy associated with the motion, and there is potential energy associated with the electrostatic interaction, and that's a total energy. We know how much it is, and we can ask, if you keep losing energy at this rate, how long will it take for the electron to come and collapse into the positive charge? Right, that's a small problem one can evaluate. In fact, maybe I will give that as a homework problem. I'll put this in the homework because it is sort of, it's a very simple calculation, but it's kind of nice because it gives you what led to quantum mechanics. If you calculate this time, how much time it takes for this electron to collapse in this sense, it comes out to be about 10 raised to minus 9 seconds, maybe 10 raised to minus 8 seconds or not. But it does not, right? Electron obviously does not collapse into the positive charge. So which means that this fails. Like, Larmor formula is correct. It can be verified in many other places. But what makes the hydrogen atom not radiate, right? That's the question that comes up immediately after you see the Larmor formula. What is it inside a hydrogen atom that stops it from radiating? And then you develop quantum mechanics just to stop that. Quantum mechanics is all because you don't want to radiate, because that's what experimentally you see. So quantum mechanics is a mechanism or a new rule, new theory you generate so that this doesn't actually happen. And this can be immediately done. So it's a small back of the envelope calculation kind of. Okay. So that's a good simple example. And that's exactly 150. Next time, basically what I will do is I'll make a simple antenna, basically take a small wire, a wire of length L. That's the simplest antenna you can make. It is called a simple antenna. And you make the current in it oscillate. Like, it's very easy to build that. You take a wire and you make the current, make it go in oscillations. It's very easy to set that up in a lab. And you get radiation on the other end. We can talk about how much radiation is there in which region, at what angle. That is how much of radiation we can talk about. But the calculation is an instructive calculation. Good to go through it, and we will do that. Okay. Any questions? Okay. So hopefully gives a feel for what's going on. Like, yeah, mathematics is a little tedious. All this one simple example has a lot of calculations, but hopefully gives you an insight into what's going on. Yeah. That is all. Thank you.
Okay, thank you.
Okay. Bye.
Bye.
Yeah.